All right. So, well, let's get into what we're going to do today, which are, we're going to start into Taylor and Maclaurin Power Series. Whoops, there we go, unfreeze, Power Series. Okay. It's not terrible, okay, really it isn't.
It's pretty bad.
It's not bad, okay.
Does it get worse?
We'll find out. I don't know.
I mean, he told us yesterday that it gets a whole lot worse.
Not worse. Just
But I didn't know if you meant
it ramps up a little bit after the quiz. We'll say, yeah.
What do you mean it ramps up?
Ramps up. Well, this isn't that bad, right? It's just, I mean, I would say the worst part about this is just it's like a lot of writing. You know, you have to like find a lot of derivatives and then put everything in, the right form and stuff like that.
I'm down for a lot of writing. It's easy.
Yeah, okay. Well, I mean, I don't know. Did you think this most recent writing has been easy?
Yeah.
No? Maddie says no, though. It is, you're right. I agree with you on that. That's right. And that's why, of course, ultimately this stuff ends up being, it's very programmable, and that's why I use computers and stuff like that. But for our purposes, we're not going to necessarily do that all the time, right? For our tests, at least, and stuff, so we need to make sure you can do it by hand, too. Just to understand the basics and fundamentals. Anyway, so our main kind of like idea here, right, has been to approximate functions using these Maclaurin and Taylor polynomials, okay? Really, it's always been Taylor polynomials. It just depends on where it's centered. If it was centered at 0, right, if we wanted to like start at 0 and build from there, that was using a Maclaurin polynomial. But then more generally, right, the Taylor polynomial centered anywhere else, it's just a horizontal shift of the Maclaurin polynomial, and so it's, similar kind of stuff there. And again, we build that by continuing to like increase the degree of our polynomial. And by increasing that degree, we can then ensure that more and more of the derivatives of our approximation match more and more of the derivatives of the actual function, right? So, but of course, those have always been kind of finite, right? So if we go back here, in the last section, we found that Taylor and Maclaurin polynomials can approximate various functions. For example, we know the Maclaurin polynomials p sub 1 through p sub 5 for the function f of x equals e to the x are as follows, right? So if you recall, okay, this is like one of the first kind of thing that we did, right? We started with like all those steps, all right? I'm not going to do the 0th one because that's silly, but we'll start with, the first polynomial was 1 plus x, right? And we said, okay, that's, approximately e to the x. Yes, bless you. And then we went one step better. We're like, okay, let's make a degree 2 polynomial. It's even closer, and that resulted in the 1 plus x, but then we added the x squared over 2 factorial. Okay. All right, and then that gave us a little bit better approximation, right? We not only matched the point at 0, bless you, we also matched the slope at 0, and we also matched the concavity at 0. Yes?
Why are we doing 9.10 before 9.8?
Great question. I think it just works out better this way. Yeah, no. Yep, that's what we're doing. It's a little funky, but I think it just works out this way. To see this. Okay. So yeah, it is a little strange we're deviating from the book, but yep, that's all. We'll get to it though. Third polynomial here, right? Well, it was 1 plus x squared over 2 factorial plus x cubed over 3 factorial, right? And again, that was a better approximation. And then the 4th degree was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and that was even better. And then one more time here, the fifth polynomial there. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4th over 4 factorial, and then x to the 5 over 5 factorial. And then was even better approximation. Okay. But of course, all of these, right, are approximations of e to the x, right? We found that the higher the degree of the polynomial, the better the approximation becomes about that center c, right? So again, this is Maclaurin. We're centered at 0. This would be slightly adjusted a little bit, right, depending on if we were centered about something else. Okay. But again, the more degrees we added, the higher the degree, the better the approximation. The more our polynomial becomes like that e to the x. Okay. So if we wanted to find the exact representation of these functions, in other words, if we wanted to find not the squiggly equals, right, we actually equals e to the x, okay? Well, we would want to increase our degree infinitely, right? Okay, infinite terms, right? If we add up all those infinite terms, then we would come up with e to the x precisely. Okay, we'd come up with e to the x precisely. All right, so what would that look like, right? So this is the definition of a power series, okay? If x is a variable, then an infinite series of the form sum from n equals 0 to infinity of a sub n times x minus c to the n, okay, and then that would result in this right here, is called a power series centered at c. And the term a sub n x minus c to the n is called the general term. Okay? So basically the name, the series that results in e to the x here, that's called a power series, right? Okay. And so that's a power series, right? And so then we can also talk about Taylor and Maclaurin power series, right? Because Taylor and Maclaurin have a very kind of like regular pattern about how we create them, right? You see this right here. You have the different derivatives of f, okay, at c over n factorial and then times x minus c to the n, right? This is essentially our Taylor formula, I guess I'll say, right, written out. Okay, there's our Taylor formula written out for us, but now just put in a summation notation. Okay, and this is called the Taylor series for f of x centered at c. Okay, and of course, a Taylor series centered at c equals 0 is called a Maclaurin series, right? So it's just taking all we've already been talking about, Taylor and Maclaurin, and now we're just putting them in the context of a series, right, with summation and stuff like summation notation. Okay, so questions on any of that so far? All good? All right. So one other thing here I want to say. So this function, okay, this is f of x is essentially equal to then this function here that we're creating. Okay. F of x, the function we're trying to approximate using the Taylor and Maclaurin power series, the function that we're trying to approximate will be precisely the infinite sum of its Taylor series. Okay. Will be precisely the infinite sum of its Taylor series. Okay. Just like we were saying here, if we kept going with this sum, this sum right here for an infinite number of terms, then e to the x would be precisely that series. Okay, so let's turn the page here. And at the top, you can see if you can find the pattern for the coefficients of the Taylor polynomials for a function, then you can extend the pattern easily for the corresponding Taylor series. Okay, so we take our Taylor polynomials, that's what we've been writing, right? A finite length polynomial, and we then come up with a pattern to then create the Taylor series. Actually, I don't need the double arrow there. We'll just do it this way. Okay. So we're going to take those Taylor polynomials, look for the pattern, and then come up with the Taylor series, right? Which is exactly what we did back when we were doing sequences and series, right? We would write out the sequence. In this case, the Taylor polynomial is like the sequence. And then we use that sequence to determine what the series pattern would be, right? What it would be. Well, I guess this is not really like the sequence because we're adding them up technically. So it's like the series and then writing the summation notation, I guess I should say. Okay, so this is like taking the series written out as a sum and then rewriting it as a summation with sigma and stuff like that. Okay, so example 1 here asks us to write the 4th degree Maclaurin polynomial for f of x equals e to the x. Okay, and so go ahead and do that. All right, this is something we know how to do. So first step, take it away, kind of thing. Write the 4th degree Maclaurin polynomial for f of x equals e to the x. Okay, so go ahead. That's something that we can do. And I'll again recommend that you write out what the fourth degree polynomial would look like here. So that would be, your f of 0. And again, Maclaurin polynomial, that means we're centered where? We're centered at 0, right? So. 30 more seconds here. 30 more seconds to write out that Maclaurin polynomial. So what? Thank you. Thank you. I feel like there's probably a place you can go where you can see like what percentage of your taxes go to different like places and stuff like that. And I feel like mine's like a teensy-weensy, you know, kind of thing. It's more like defense. That would be like a big thing. Something like that.
I did all my math.
Yeah.
They consider appreciation bet.
And it's weird when I pay taxes, I'm paying myself. I'm like, thank me very much.
That's a good way to, that's a positive way to think about paying taxes.
Again, it's like probably cents of the, you know, thousands that I pay, so.
It takes a whole lot to have positivity like that to pay taxes. It takes a whole lot.
Okay. There's our Taylor polynomial, right? You probably didn't even need to write this part out, but I just did it because, hey, why not? Okay? So there's our fourth degree Taylor polynomial, and the idea is we're now going to take this, right, and come up with the kind of like pattern here, okay? And that is what we call the general term, I should say. So the pattern, you know, kind of like formula, okay, which is really known as the general term, right? Because that's the next thing we were asked to find, right? That general term. That's new today. All right. And a good place to start here would probably be with n equal to what? I would say n equal to 0 here. Okay. So if we look, right, that would mean this is our n equals 0 term, this is our n equals 1 term, this would be our n equals 2 term, this would be our n equals 3, this would be our n equals 4, so on and so forth. Kind of terms there. Okay. So, what do we have going on here? What is our general term going to equal? Well, we have a fraction, right, in these, 1 over something, right? It's always 1 over something, so that means we can put it, a 1 in the numerator of our fraction, over, and then what should be in the denominator of our fraction? N factorial, right? As we proceed here, right, even 0 factorial will still give us a 1, so it'll be 1 over 1. So it's, yeah, 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, so on and so forth. And so, yeah, we probably just want n factorial in the denominator there. Okay? But is that it? Is there anything else that we have as part of our terms here? X to the n, exactly right. Okay? Or if you like to put it all together, you can say x to the n over n factorial. So either one of those there. So that's the general term that we just found there, general term. All right. And also the Maclaurin series. So that means we need to use sigma notation. So then the series will just be sigma notation here. Sigma, sum from n equals 0 to infinity of what? The general term, the thing we just found here. Okay? X to the n over n factorial. And that is precisely equal to e to the x. Okay, that is the sum e to the x there. Okay, and again, this is not something new. We've already kind of talked about this earlier, right? In an earlier section, we did this. Okay, not that exactly. All right. And so now, what we're going to do over the next couple examples here is come up with some. I guess polynomials, some series, I guess, some series for different, common functions. So here we just wrote the power series, Maclaurin series, okay, for e to the x. Now for the next function, we're going to be looking at ln of x, natural log of x. Okay. Now for the natural log of x, we're not going to be centered at 0. And why would it not be a good idea to center our power series at 0 for the natural log of x? Right, because you can't take the natural log of 0, right? The natural log of 0 does not exist, and so we have to center somewhere else. So we'll use 1. Okay. All right, to build this polynomial. All right. So again, you guys go ahead, write the fourth degree Taylor polynomial for the natural log of x centered about c equals 1. Okay. So go ahead and do that. Right. That's something you guys are all quite capable of here. So. second, I'll write out the. Now remember, since this is a Taylor series, right? It's going to be x minus 1, right? Or x minus c, so x minus 1 for our terms there.
Do you want us to do the pattern formulas?
Yeah, I was going to say, so if you feel like you can get the general term, all right, if you feel like you can get the general term, go ahead. I will recommend, if you want to, you might want to help yourself out by simplifying those factorials, like the fractions with the factorials and stuff like that, like I did, okay, on my third step there. So leaving the factorials in there, that's cool, but if you simplify the factorials with the factorials and the fractions and stuff, it'll help you, I think, see the pattern, or make a more simple pattern, I guess I'll say. So, yes. Like 30 more seconds here or so? About 30 more seconds. So close. I mean, notice here with the positive, negative, further derivatives. So you use additional derivatives. So really, like, ideally you want to have 4 non-zero terms, but because you kind of like alternating every time out to 0, you need to do more terms than just. But the nice thing is that it repeats itself, right?
What we're supposed to do.
Okay. All right, so there again, I already had most of the work up there. I just wrote the words general term for you, okay? So, what are some aspects we see here with every term? Well, we start at 0, so that's something to consider, all right? And in fact, we probably shouldn't start, we probably should not consider 0, okay? We're just going to start with our first like actual term here, our first kind of like non-zero term, all right? We're not going to focus on trying to make 0 because 0 doesn't really affect the sum anyway. So it's really just a matter of starting here and then building on. And so I'm going to say n equals 1, okay, for our first term there. And then this will be n equals 2, n equals 3, n equals 4, so on and so forth. All right? So with that in mind then, what are some aspects for our general term that we need to see? Okay, we need to see alternating, and specifically we need when we plug in 1, we need our term to be positive or negative. Positive, right? And so if I take -1 and raise it just to the n, will that result in a positive first term? No. So what do I have to do to adjust this to make my first term be positive? N plus 1 or n minus 1? Doesn't really matter. You just got to offset it by 1. Okay. All right, what other aspects do we need to include here? I see a fraction, right? How can we account for this fraction? 1 over n. Okay, and then I also see kind of like our polynomial kind of term there, our algebraic term, and how do we account for that? X minus 1 to the n, exactly right. Oops. Okay. Like so. Okay, so there's our general term. Okay, a piece at a time there. So then our series will be the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 1 to the n all over n. And that is exactly equal to the natural log of x. Okay, that is the natural log of x. Okay, no squiggles here. Okay, no approximately equals to. That is precisely the natural log of x. All right, questions on any of that? All right, no, moving on here. All right, so then next we're going to tackle sine and cosine, okay? And these can be, again, written. Yep, good, we're almost there. So let's take a look here at sine, and then maybe I'll have you guys do cosine, okay? So write the Maclaurin series, meaning we are centered at 0. Okay, so that's nice. All right. So again, in order to do this, we're going to try and write out the first couple terms here, all right, of our Maclaurin polynomial, all right? So let's do this here. So we'll try p sub 4 here and see how it goes. So that would be, f of 0 plus f prime of 0 over 1 factorial x to the 1 plus f prime prime of 0 over 2 factorial x to the 2 plus f prime 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 of 0 over 3 factorial x to the 3 plus f fourth derivative of f at 0 over 4 factorial x to the 4 plus dot dot dot. You get the idea, right? Okay. So there's our Maclaurin polynomial, and so we need to come up with f at 0, f prime at 0, f prime prime at 0, f prime 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 at 0, f, well, fourth derivative of f at 0, so on and so forth. So we got sine, derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine. The derivative of negative cosine back to positive sine, right? Because the derivative of cosine is negative sine, so it's negative negative sine becomes positive sine of x. All right? And if we evaluate, okay, these at 0, all right, what are we going to end up with here? Well, sine of 0 is 0. Cosine of 0 is 1. 0 again for negative sine. -1 for negative cosine. And then 0. Okay? And we run into some problems here because f of 0 cancels out, right? Goes away. F prime prime of 0, it's going to be 0, so that whole term goes away. And then f, the fourth derivative of f at 0 is 0, so that term also goes away. And so we end up with only 2 terms. And that can be kind of tricky to come up with, you know, kind of more or to come up with a pattern only having 2 kind of results. All right? Because right now all we would have is 1 over 1 factorial x to the 1, and then minus 1 over 3 factorial x to the 3. Okay? Maybe we have enough information there, okay, to kind of figure it out. Maybe, but we should probably try and do some more. And so I'm going to try and get 2 more non-zero terms here. So I'm going to do the 5th derivative, which is going to be cosine of x, and that's going to give me another 1. So there's another term. The 6th derivative, though, derivative of cosine, is going to be negative sine of x. That's going to give me 0 again, so nope, no more terms there. But then if I do the 7th derivative of negative sine will be negative cosine of x, and so that will give me then a -1. And so, phew, we got 2 more terms. All right, that happened in the 5th derivative, so that means we're going to have a plus 1 over, what will be my next term here? If it's the 5th derivative, that means it's 1 over what? 5 factorial x to the 5th. And then since the next one happened in the 7th, so we skipped the 6th term, the next one happened in the 7th term, so what will that one be? Minus 1 over 7 factorial x to the 7th. So we end up having to look at the 7th Taylor series here, 7th degree Taylor series, Taylor polynomial, I'm sorry. 7th degree Taylor polynomial, Maclaurin polynomial, because of the just zeros and stuff like that, okay? Just get the pattern down. Okay. You, again, since it doesn't specify here how many terms to do, you do as many terms as you think you need in order to get it. maybe after the first 3 you looked at it and you're like, I think I get the idea, but you know, it's a good idea at least to, I would say 4 terms are a good, you know, way to go. Okay. So we'll start at n equals 0 here for this one. So they'll say that term's n equals 0, that term's n equals 1, that term's n equals 2, that term is n equals 3. Okay. We're not going to be skipping, you know, our n's aren't going to skip here. We need to count. Because for a summation, you have to count from your starting point up by 1 each time, right? So if we start at 0, we have to go then to 1, to 2, to 3, okay? You can't like skip, you know, your counter with a summation. So with that being said then, let's write out our general term, and then we'll write out our series. All right? So what kind of behavior do we see happening here? Okay, it's alternating, okay? And we need the first term to be positive. And so in this case, since I'm starting with n equal to 0, I'm going to take -1 and raise it to what power? Just n, right? Just n is sufficient there because it's n equals 0. So for -1 to the 0 will become a positive 1. That would make us our first term positive. Okay. Now we have some other aspects, right? We have fractions, and they're all 1 over something. So we'll have times 1 over, and then what should be in our denominator here? Okay, so yeah, it's a little bit trickier, right? Because we're not doing every term. So we can't just say n. What do we know our denominator has to have, for sure? It's got to have a factorial, all right? So we're going to have something factorial. All right? Well, how are our numbers changing? We go from 1 to 3 to 5 to 7. So they're going up by what? 2 each time. So we're repeatedly adding 2. What does repeatedly adding 2 mean? Multiplication, so 2n, right? But for my first term, if I have a 2n, and I plug 0 in for n, 2 times 0 is 0, but I need it to be 1. So what do I have to do? 2n plus 1. Exactly right. And there it is. 2n plus 1. That's it. Okay? So the pattern was, our factorial was adding 2 each time. That repeatedly adding 2 is like a multiplication, right? Times 2, but then we had to correct just for that first term to make sure we do get the 1. But then for our next term, right, when n is 1, 2 times 1 is 2, plus 1 is 3, okay? 2 times 2 is 4, plus 1 is 5, so on and so forth. You get the idea, okay? And we have one more aspect we haven't covered yet, the x's. it is x to the exact same thing, exactly right. Our powers, it goes from 1 to 3 to 5 to 7, so they're increasing by 2 each time. Repeatedly adding 2 to our power is 2 times n, but then we have to add 1, so it's 2n to the 1. Okay. If you do go on to do any more mathematics, you know, in your like college careers and stuff like that, you'll end up probably taking a course called number theory. In which, you know, you kind of like, well, you work with numbers, right? And it's like,
Wow.
you know, different sets of numbers, like, you know, the integers, whole numbers, and you talk about like different bases too for your numbers too. Like, so if you ever heard like a binary, right? You like learn how to do arithmetic in binary. You learn how to do arithmetic, you know, in like hex, I guess, which is base 6 and all that stuff, which is important for like computers and things as well. But another aspect you'll sometimes do is examine and prove properties of even and odd numbers. And a typical way to represent an odd number is through this. A generic odd number will be 2n plus 1, right? Because, well, the 2n will guarantee your number is even, right? Because twice anything, it's always going to be even. And then you add 1 to it, now you're guaranteed it's odd. So a generic odd number, 2n plus 1, is what you generally use there. All right? So anyway, perfect. There's our general term, and so we'll just put that into a series and we'll have our answer. So negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And that is sine of x. Okay. Which is, again, is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. You get the idea. Okay. Summed up nicely. So why don't you guys go ahead then and try cosine, right? We did sine together. Try cosine. I think you'll, of course, you know, from all the other stuff we've done with sine and cosine, you see how they're like related but not the same. You'll see something similar happen here. Yeah, so I'll give it a try. All right. Give it a go. I guess I'll leave that piece up there. And I'll give you a tip here. You're going to want to have you're going to want to write the eighth degree, or 6th degree. I mean, you could probably get away with 6, but 6th or 8th degree Maclaurin polynomial here. Okay, 6th or 8th degree Maclaurin polynomial. So go up to power 6 or power 8, right? That's my little hint. And again, since it's Maclaurin, remember we are centered at 0, right? We're centered at 0 there. see that you recognize that you are alternating here, right? Right here, right? So, but this is not going to account for the alternating piece because it's always going to be an even exponent. So you need to. It should. Negative. Oh, I see. This should be positive. Yeah. So cosine, negative sine, cosine, positive sine. Because every cosine is negative sine, so it's going to be negative. There it is. Good job. Yes. Oh, would it be the same thing? I see. Sorry.
You know what kind of mess that is? The one where you put the multiplication sign and x, 9 is like 20. I miss those days. Really?
I think so. Yes. But I think the way we're going to be generally working with things is starting with n equals 0. But I believe this would be the equivalent. Yes. Yes. All right, 30 more seconds here, so about 30 more seconds. 30 more seconds. EC.
So what, if I, this be n equals 0?
So yes, I would start with n equals 0.
Did I even do that somewhere?
I mean, let's see. I think it's helpful.
Okay.
Because again, 1 isn't a whole lot of information, and so that's why the 4 terms then going, so, but yeah, that's why I said 6th degree or 8th degree,
Thank you.
Yep. And again, you won't be like deriving these on quizzes or tests. The idea is you'll have them. You know what I mean? Like you'll know them. Okay. Because ultimately we're going to be manipulating these in order to rewrite them. Stuff like that. All right, just a little bit longer here. A few more seconds. And like another 30 seconds. I'll say. Give people a chance to think about it. Okay. So there's our general term. starting with n equals 0 there, from negative 1 to the n over 2n factorial there, times x to the 2n. And so then we can finally finish this off by saying that cosine of x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, all over 2n factorial. Okay, which again is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus dot, dot, dot. You get the idea, right? There is the Maclaurin series for cosine of x. It is x to the 2n. 2n, yeah, factorial. And so, of course, 2n plus 1 is the generic representation of an odd number. 2n is the generic representation of an even number, right? Because twice a number will always be even. Or twice an integer, twice a natural number will always be even. All right, so turn the page. And so we're going to stop here and after summarizing these Maclaurin series, okay? So the Maclaurin series that you must know, right? That you must know. Well, e to the x. Okay, so these you're going to need to know, like you know your derivative rules, like you know your integral rules, okay? Like a lot of the other things you need to know in this class, right? But this is it, okay? So we're going to re-summarize those four, actually the three. The natural log we're not going to worry about, actually, okay? But e to the x, okay, is going to be 1. So remember that was the sum from n equals 0 to infinity of x to the n over n factorial, okay? Which if we write out a few terms there, it's 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. All right, then we talked about sine as well. That's another one we'll need to know. And that is also the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So that was your x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. You get the idea. And then cosine of x, which is exactly the sum from n equals 0 to infinity of negative 1 to the 2n times x to the 2n over 2n factorial. I was going to say, I remember I was like, yeah, yes, thank you. I was like, that's not right. Sorry, just n there. Because like I just talked with Matthias about something, and I was like, that's not going to be right. So, all right. So again, sorry, negative 1 just to the n, x to the 2n factorial, and that's equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. You get the idea there. Okay. And there's one other Maclaurin series that we will need to know, and it's sum, right? So the sum of this series was e to the x, the sum of this series was sine of x, the sum of this series was cosine of x. The sum of the fourth series that we'll need to know is this. Now we didn't talk about that one today, but we've talked about it in the past. What is this? This is the sum of what kind of series? Geometric. Yeah, okay, so we're going to count that as a power series there. Okay, so some little tips or tricks about how to help you remember these things. Okay, so for example, here in e to the x, you can think, it's all factorials, not alternating. Okay, so all factorials not alternating, right? This is like, it's 1 over 0 factorial, x over 1 factorial. So it's 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, so on and so forth kind of thing. Okay, for this one, for sine, it's odd powers and factorials. Okay, so both the powers and the factorials are odd, and that's all you use, are odd powers and odd factorials. Okay, and of course it's alternating too. Okay, and then for 3, or for cosine, right, that's your even powers and even factorials. Okay, and again, that is also alternating. And then geometric, well, that's, it's geometric series there, so. If you want help remembering, that sine is, the odd powers and factorials, and cosine is even powers and even factorials. Remember, what does it mean for a function to be even or odd, right? Doesn't an even function, it's symmetric about the y-axis, right? And cosine is symmetric about the y-axis, right? Sine, okay, it is symmetric if you have rotational symmetry about the origin, right? Which is exactly what an odd function is. So cosine's even, sine's odd, and so that can help you also remember, which, powers and factorials go with which one too. Okay, I'm not sure. I can't necessarily say that that's exactly why they end up that way, but I'm thinking that might be, or it might be related at least. I'll say, because you're using an even degree polynomial to approximate it here, so possibly. Okay, so that can help you there. All right, and so we'll stop right there for now, and we'll come back tomorrow and hit example 5 and stuff like that. All right, so we'll stop there. I'll get you guys started on your assignment. I'll also, if I have time here, I'll show you my problem here. I think I should, but because you have a pretty good amount here.